Hello, my name is Cayden Lloyd. I will be briefly talking about results from a study looking at sediment sourcing for the Cottonwood River and John Redmond Reservoir here in Kansas. So, reservoir sedimentation is a global issue and has been a big deal in the U.S. and Kansas over the last 30 years or so. It has caused a huge loss of reservoir storage capacity for many reservoirs, and multiple reservoirs in Kansas, including John Redmond, are expected to lose more than 50% of their original storage capacity just in the next decade or two. So most regional management agencies here assume that the dominant contributor to this sediment deposition in reservoirs is stream bank erosion, which has led to lengthy and expensive projects on stream bank stabilization, um, including projects here on the Cottonwood River, in which drains into the John Redmond Reservoir. So we are trying to test that assumption by identifying source contributions for this reservoir using a model called sediment fingerprinting. So we identified three sources: stream banks, cropland, and grassland. And then we looked at three different versions of the mixture of those sources. So first, we're looking at lake bed samples from John Redmond. We're also doing suspended sediment samples from discrete storm sample collection on the Cottonwood River. And we also have time integrated sediment trap samples on the Cottonwood River as well. So the model itself, there are a couple approaches, but most sediment fingerprinting models solve for the same series of equations. So first, we say that the sum of our source fractions adds up to 1. Basically, we're just not missing any sources. And then also the sum of the source fraction times the tracer concentration of the sources adds up to equal the tracer concentration of the mixture. And a tracer is basically just a characteristic of the sediment. So we look at 29 different tracers. We have to make sure they are both informative and conservative to use them. So the only four tracers that passed both of these rules were sediment nitrogen, our isotope ratio for nitrogen 15, barium, and plutonium. And then here we had do a PCA analysis. This basically is just a way of interpreting the data in a couple of variables. And it basically just confirms that our sources are different from each other, so we can tell difference, and that our mixtures, which are these little boxes, lie within those sources, so we're not missing any important sediment sources. So the model produces fractions for each of our mixtures. Down here you can see that our lake samples, crop is actually the most dominant source fraction. But bank increases as you go from lake to storm to trap. Now, the reason for this is that most sediment transported to reservoirs happens during infrequent out-of-bank floods. So that is this tiny little sliver of storms that happens up here, where most of the sediment is eroded on the cropland that's in the river delta on the Cottonwood River. Our discrete storm samples are kind of a medium intensity sample. So these are still storms where it's flooding uplands, but not with the same intensity as our out of bank floods. And then our time integrated samples, these boxes, are over a longer period of time and on average have a much lower flow. So it kind of makes sense that most of the sediment is from cropland, since most of it is transported during these out-of-bank floods. As you can see here, this is mostly cropland in the river delta. All of that gets pushed down to John Redmond Reservoir, which explains why cropland is the dominant source fraction, despite the assumption that stream bank erosions are. So this really just tells us that that assumption is not true. Stream bank stabilization can still work if you're trying to stop it locally, but as far as stopping deposition in reservoirs, local management agencies should really look at implementing practices that reduce erosion on uplands, especially on cropland. So that's all the time I have, but hope this was informative and thank you for your time.